Welcome back to our deep learning series. Today we're diving into one of the most important adaptive optimizers, Adagrad. But first, let me ask you this. Have you ever wondered why your neural network training gets stuck in valleys, oscillates wildly, or converges painfully slowly? Traditional optimizers like STD use the same learning rate for all parameters. But what if different parameters needed different learning rates? That's exactly where adaptive optimizers like Adagrad come to the rescue. They automatically adjust learning rates for each parameter based on historical gradients. Ready to master Adagrad? Let's get started. Adagrad stands for Adaptive Gradient Algorithm, introduced by Ducci, Hazan, and Singer in 2011. Here's the key insight. Imagine you have two types of parameters in your network, some that get updated frequently with large gradients and others that rarely get updated. Adagrad gives smaller learning rates to frequently updated parameters and larger learning rates to infrequently updated ones. The core idea is simple. Accumulate the squared gradients over time and use this information to scale the learning rate. The formula looks like this. Theta of t plus 1 equals theta of t minus eta divided by square root of gt plus epsilon times g of t, where gt is the sum of squared gradients up to time t, eta is the initial learning rate, epsilon prevents division by 0, and g of t is the current gradient. Think of it like driving a car. If you've been accelerating frequently on a highway, you become more cautious with the gas pedal. Similarly, Adagrad becomes more conservative with parameters that have seen large gradients. Let's break down exactly how Adagrad works step by step. Step 1. Initialize. We start with 0 accumulation, G0, for all parameters. Step 2. Compute gradients. Calculate gradients normally using backpropagation. Step 3. Accumulate squared gradients. This is where the magic happens. Step 4. Adaptive update. Update parameters with scaled learning rate. Let's see this in action. Imagine we're optimizing a function with two parameters. Parameter 1 has consistently large gradients, while parameter 2 has small, sparse gradients. Watch how Adagrad automatically gives parameter 1 smaller effective learning rates over time, while maintaining larger rates for parameter 2. This prevents overshooting in sensitive directions while maintaining progress in others.
So, when should you reach for Adagrad? Here are the key scenarios. Scenario 1. Sparse data. Adagrad shines with sparse features. Think recommendation systems, NLP with large vocabularies, or any dataset where most features are 0 most of the time. In word embeddings, rare words get infrequent updates. Adagrad ensures these rare words still learn effectively when they do appear. Scenario 2. Different feature scales. When your features have wildly different scales, like age 0 to 100 versus income 0 to 100,000, Adagrad naturally handles this. Scenario 3. Early training phases. Adagrad works great in early training when you want aggressive adaptation, but be careful about long training runs. Avoid Adagrad when training for many epochs, learning rate decay becomes too aggressive. You need consistent performance across long training. Working with very large models where memory for GT becomes expensive. Adagrad was groundbreaking, but it had issues. Let's explore the improved variants that followed. The problem: aggressive learning rate decay. As training progresses, the denominator, root GT, keeps growing, making learning rates smaller and smaller until they virtually stop learning. RMSPR 2012. Hinton's solution: use exponential moving average instead of cumulative sum. Added Delta 2012 goes one step further, eliminates the need for a default learning rate entirely. Adam 2014, the popular combination RMSPR's exponential averaging plus momentum. Each variant addressed specific limitations while keeping Adagrad's core insight about adaptive learning rates. Time for some hands-on coding. Let's implement Adagrad from scratch and then see how to use it in popular frameworks. This is a pure NumPy implementation. This is the implementation in PyTorch and TensorFlow and Keras. What makes Adagrad special? Let's count the advantages. Advantage 1. No manual learning rate tuning. Forget about manually adjusting learning rates for different parameters. Adagrad does it automatically. Advantage 2. Handles sparse data like a pro. In recommendation systems or NLP, where most features are 0, Adagrad ensures rare features get their moment to shine. Advantage 3. Fast initial convergence. In early training, when gradients are large and diverse, Adagrad converges faster than SGD. Advantage 4. Scale invariant. Whether your features are in range 0 to 1 or 0 to 10,000, Adagrad adapts automatically. No more manual feature scaling headaches. Advantage 5. Simple and intuitive. The algorithm is straightforward to understand and implement. No complex hyperparameter tuning required.
But Adagrad isn't perfect. Let's discuss its main limitations honestly. Problem 1. Aggressive learning rate decay. This is the big one. As G sub t accumulates squared gradients, the effective learning rate approaches 0. Eventually, the model stops learning entirely. Since G sub t is monotonically increasing, the square root of G sub t approaches infinity, making the learning rate approach 0. Problem 2. Memory intensive. Adagrad needs to store G sub t for every parameter. For large models with millions of parameters, this doubles memory usage. Problem 3. Not suitable for long training sessions. While great for initial convergence, Adagrad struggles in long training sessions due to the decaying learning rate. Problem 4. Sensitive to initial learning rate. Unlike what we'd hope, the initial learning rate still matters quite a bit, especially for the first few iterations. The bottom line? Adagrad was revolutionary and introduced adaptive learning rates to the world. But for most modern applications, you'll probably want Atom, RMS prop, or other variants that address these limitations. Let's wrap up with some practical tips for using Adagrad effectively. Tip 1. Use higher initial learning rates. Since Adagrad will decay the learning rate automatically, start with LR equals 0.1 or even LR equals 1 for sparse data. Tip 2. Perfect for sparse features. If you're working with sparse data, definitely try Adagrad before other optimizers. Tip 3. Monitor learning rate decay. Keep an eye on effective learning rates. If they become too small too quickly, switch to RMS prop or Atom. Tip 4. Consider modern variants. For most applications, Atom or Atom W might serve you better, but understanding Adagrad helps you appreciate why. That's Adagrad in a nutshell. This optimizer laid the foundation for all modern adaptive optimizers. Next week, we'll dive into RMS prop and see how it solved Adagrad's aggressive decay problem. If this helped you understand Adagrad better, smash that like button and subscribe for more deep learning content. Drop your questions in the comments below. Thanks for watching, and I'll see you in the next video.